The magnetar name comes from the fact that certain neutron stars, for reasons that are still unknown, have the strongest magnetic fields in the universe.
The magnetic field of a magnetar is exceptionally strong. It can be 1,000 trillion times as strong as Earth's magnetic field. That's fantastic.
The magnetic fields are so intense that if a magnetar suddenly appeared halfway between the Earth and the Moon, it would be strong enough to disrupt all of the electronic equipment on the planet, including stripping the information off every credit card on Earth. And the reason magnetar flares are so powerful is that the magnetic fields around certain areas of the star sometimes twist themselves so much that they can't twist anymore, and suddenly release like a spring.
The process is similar to a solar flare in that it's the magnetic field that's giving rise to the energy. It's the shaking and tangling and sometimes the reconnection of lines of force going in different directions that gives the energy that powers the flare.
But unlike planetary collisions, where kinetic energy dominates, magnetar flares shoot out most of their energy as electromagnetic radiation. In other words, light. And one magnetar flare in particular was strong enough to blind satellites orbiting Earth from 50,000 light years away. The biggest blasts in the universe dwarf anything we can imagine on Earth. We're already billions of times beyond the entire nuclear arsenal of the world. Number 6 on our countdown are the flares that burst from incredibly magnetized neutron stars, known as magnetars. And one of the most powerful ever observed from Earth released as much energy in just over 1/10 of a second as our sun does in about 100,000 years. The blast in 2004 came from a magnetar known as SGR 1806-20 in the constellation Sagittarius. It's about 50,000 light years away from Earth on the far side of the Milky Way.
It was incredibly powerful. All that energy came in 1/10 of a second. It blasted the detectors and satellites that happened to be flying around up there. In fact, it was the brightest blast ever seen from an object outside our solar system. And yet, it was 50,000 light years away.
But what does brightness have to do with the power of a blast?
So I'm standing in a dark room here, and now I'm going to turn on a light bulb. How bright that light bulb appears to me depends on 2 factors. It depends on how intrinsically powerful or luminous the light bulb is, its wattage, how much energy it puts out per second, and it also depends on the distance of the light bulb from me. When I'm close to the light bulb, I see that the light bulb is bright. If I move a factor of 2 farther away, then in fact it looks a factor of 4 fainter. That's the inverse square law of light. The power of the light bulb has remained the same, but by being twice as far away, I get only 1/4 of the light reaching my face and my eyes. Astronomers measure the apparent brightness of the star or the explosion. They figure out its distance through some other technique, and from those 2 variables, they figure out the power or the luminosity of the source.
That light is released not just in visible wavelengths, but across the electromagnetic spectrum. And anytime researchers detect gamma rays, like they do in magnetar flares, they know it must be a big blast.
Gamma rays are a type of light, but a much more energetic light than we see with our eyes. So the spectrum of light that we're familiar with goes from very low energy and through the visible part of the spectrum, the light that we see, all the way out through X-rays into this extremely high energy component of light, which is called gamma rays.
Even a 1/10 of a second short gamma ray flare, like SGR 1806-20, would still be able to fry the Earth with radiation from many light years away, as long as the full force of the flare was aimed at Earth. But not all of the biggest blasts in the universe are over in a fraction of a second. Number 5, the 100-million-year blast. 2.6 billion light years away from Earth, a supermassive black hole, billions of times the mass of our Sun, has been wreaking havoc in the center of a cluster of galaxies. Known as MSA 735, it's been shooting out 2 continuous jets of particles in opposite directions. Scientists believe the jets have been raging for the past 100 million years, punching 2 huge bubbles into the surrounding galaxies.
MSO 735 really is the prototypical example of a black hole blowing bubbles. What we're seeing here is giant cavities being evacuated by these powerful jets. So they transport vast sums of energy down from the black hole out to huge distances, maybe about 1 million light years or so.
1 million light years is 10 times wider than our Milky Way galaxy, which means these jets are powerful enough to create 2 very big bubbles.
The total energy within these 2 bubbles is stupendous, far exceeding any other amount of concentrated energy that we know of in the universe. However, it must be remembered that the energy was released over 100 million years. That means that per unit of time, the total amount of energy released wasn't all that big.
Still, the jets are strong enough to shoot the particles out at millions of miles an hour, about 1/4 of the speed of light. The jets and resulting bubbles only come from about 1% of the most massive black holes in the universe. That's because the forces near these monsters are so huge that instead of swallowing everything, they actually end up pushing some particles away.
It's important to emphasize that these giant explosions are not the explosion of the black hole itself, but rather an ejection of particles from near the black hole, the vicinity of the black hole. By colliding with one another, they can, in some cases, be ejected out of the vicinity of the black hole.
But how can this 2-sided blast possibly keep going for 100 million years? It's all a matter of how much cosmic stuff is available, as planets and suns are stretched and ripped apart down to their very atoms and drawn towards the black hole.
So these jets that we've estimated have been going on for about 100 million years still have a huge amount of fuel available to them. That process can go on for an extremely long time, hundreds of millions of years.
Now, imagine taking a big chunk of that energy and releasing it in less than 2 seconds. That's what researchers believe happens in blast number 4. Short gamma ray bursts.